Okay, so in this lecture, we're going to analyze the linear transformations by using the diagonalization. So before we get started, well, let's pause the video and try out the warming up question, part A and part B, before I give you the solutions. Okay, so let us work on these problems together. So basically, we have the set B as the basis for R2, and we want to find, or we want to change the coordinate from B to the standard basis, and the standard basis to the B coordinate. So how do we do that? Well, we can change the coordinate by multiplying the change of coordinate matrix, which is given by P sub B to E, where E is given by the standard basis, 1, 0, and 0, 1. And if you multiply this to the B coordinate of x, then we get the vector x. So this equals to, so we have to bring the basis over here. So that gives you 2, 1, and 1, negative 1. And the B coordinate is given by 1, 3. So if you multiply these, then we get, I guess, 5 and negative 2. Similarly, we can find the B coordinate by multiplying the inverse matrix of P sub B to E. So this equals to P sub B to E inverse times x, where this equals to 1 over, so the determinant is given by negative 2 minus 1, and the adjugate is negative 1, 2, negative 1, and negative 1. And you multiply this by 3, 0. So this gives you 1 over negative 3 and negative 3, negative 3, which equals to 1 and 1. So what we are going to do in this section is, so suppose that you have a vector space V and W, and let's say you have a linear transformation from V to W, which is given by T. So the point X is sent to T of X inside W. So here, T is a linear transformation from V to W, and V and W's are finite dimensional vector spaces. And let's say B to be a basis for V and C be the basis for W, then you can certainly take the B coordinate of X. Then this will give you a coordinate, say X square bracket sub B, that sits inside R to the N. And at the same time, you can take the C coordinate of T of X. Then this will give you the square bracket T of X sub C that sits inside R to the M. So what we want to do is, we want to go from here to there. So basically what you want to do is, you want to do the linear transformation and the change of basis simultaneously. So how do we do that? Well, we can accomplish that by multiplying the matrix M, where M is given by T of B1 in C coordinate, T of B2 in C coordinate, so on until T of B sub N in C coordinate, where B is given by B1 through Bn. And we call this matrix M as the matrix for T relative to the basis B and C. So intuitively, so this M moves your vectors to W and change the coordinate into C simultaneously. So suppose that B is given by B1 and B2, which is a basis for V, and C to be C1, C2, and C3, which is a basis for W. And let's say T to be the linear transformation from V to W. So in this case, we have the dimension of V equals to 2, and the dimension of W equals to 3. And let's say T of B1 and T of B2s are given in this way. And let us find the matrix M for T relative to B and C. So first of all, M is given by, so T of B1 in C coordinate and t of b2 in C coordinate. And to get these two column vectors, we have to take the coefficient or the weight for the given linear combination. So what it means is t of b1 in C coordinate equals to 3, -2, and 5, and t of b2 in C coordinate is given by 4, 7, and -1. So this gives you m equals to 3, -2, and 5, and 4, 7, and -1. So in this case, v and w are not in the same dimension. So for that reason, our matrix M is not a square matrix. So the number of columns corresponds to the dimension of the domain, and the number of rows corresponds to the dimension of the range. Okay, so let's look at another interesting example. So let's say V to be the set of polynomials of degree less than or equals to 3. So it is spanned by this set. And P2 to be the set of polynomial of degree less than or equals to 2. And T to be the linear transformation, which is given by the differential operator. So this means that, so for example, like if you put, say 2t squared plus 1 into t, then this will give you the derivative of this function that equals to 4t. So let's pause the video and try to find the matrix of t with respect to the basis given by B and C. Okay, so let us work on this problem together. So basically, let us let this one to be B1, and this to be B2, and the third one to be B3, and the last one to be B4. Then T of B sub 1 equals to, so the derivative of the constant function is 0, or you can write 0 as 0 times 1 plus 0 times t squared plus 0 times, well, I think 0 times t plus 0 times t squared. And this gives you t of b1 sub c equals to just a 0 vector. And if you do the same thing for b sub 2, then the derivative of t equals to 1, or in other words, this equals to 1 plus 0 times t plus 0 times t squared, where this gives you the c coordinate for t of b2 equals to 1, 0, 0. And similarly for b3, well, if you take the derivative, we get 2 times t. So this gives you the c coordinate equals to, I guess, 0, 2, and 0. And for t4 or b4, we get 3t squared. Or in other words, we get the c coordinate of b4 or t of b4 equals to 0, 0, and 3. So using these four facts, we can build the matrix M by using them as the column vector. So M should equals to 0, 0, 0, 1, 0, 0, and 0, 2, 0, and 0, 0, 3. Okay, so we got the answer. But what does this really mean? So if you apply this matrix to 2t squared plus 1, so for example, like if you multiply M, which is given by 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3 into, so 2t squared plus 1 is equivalent to have like 1, 0, 2, and 0. Then this gives you, I guess, 0 and 4 and 0, or this is the same as the c coordinate of 4t. So indeed, multiplying this gives you the derivative of the given polynomial. So let's look at another example of that kind of stuff. So suppose that t is the linear transformation from P2 to P2 that is given by this thing. So let's pause the video and try to find the matrix representation of t relative to the standard basis B. Okay, so let's work on this problem together. So basically, again, you apply the basis vector into the linear transformation. So we have to identify t of 1 and t of t and t of t squared. So t of 1 equals to, so in this case we have a0 equals to 1 and a1 and a2s are 0. So that gives you 5 plus, I guess, just t. So this gives you t of 1 in b coordinate equals to 5, 1, and 0. And t of t, well, this, we have a sub 0 equals to 0, a1 equals to 1, and a2 equals to 0. So if you plug that over there, then we get negative 2t plus, I guess it should be 8t squared. So this gives you t of t sub b equals to, so we don't have any constant term, and we have negative 2 and 8. And for t squared, we have a sub 0 equals to 0, and a1 equals to 0, and a2 is 1. So that gives you, I guess, 3t squared. So if you calculate the b coordinate of this matrix, then you will get 0, 0, and 3. So if you cook a matrix using these as the column vector, then we get m equals to 5, 1, 0, 0, negative 2, 8, and 0, 0, 3. And this is called as the B matrix for T. So in this way, we can analyze all kind of linear transformation using the matrix representation of the given linear transformation. So let's recall the definition about the similarity. So two matrices A and B are similar if there's an invertible matrix P, such that we can write B equals to P inverse times A times P. And this is really important when you analyze the linear transformation, because similar matrices gives you sort of the same linear transformation with respect to different bases. So let us see when A is diagonalizable, or in other words, A is similar to the diagonal matrix. And let's see what is the matrix of T with respect to the eigenbases. So basically, T is a map from Rn to Rn that sends a point x to A times x. Then you can certainly apply the, so let's say B to be the set of eigenvectors for the given matrix A. So B sub 1 through B sub n are eigenvectors. Then we can take the B coordinate of the given vector that gives you a square bracket x sub B. And you can do the same thing for A times x. So if you take the B coordinate again, then this gives you ax in B coordinate. Then we are interested in the matrix representation for the given linear transformation T. So one thing that you can observe is, well, we can go from the B coordinate to the standard basis by multiplying the change of coordinate matrix, which is given by P sub B. And you can go from here to there by multiplying P sub B again. But we know that P sub B is given by the basis vectors, which is given over here. So it is B sub 1 through B sub n. But note that P sub B consists of column vectors as the eigenvectors. So this is in fact the same as the matrix P that appears over here. So here the point is going from here to the right side is the same as you go down and go right and go up again. So basically this part corresponds to multiplying A into the given vector x. But detouring is like you first multiply P inverse to x, and you multiply by T in B coordinate, and then you multiply by P again, or this is equivalent to have A equals to T sub B, P to the inverse. But we already have similar thing above over here, so we can conclude that T sub B equals to the diagonal matrix D. So here, the lower horizontal map is multiplication by the diagonal matrix D. So theorem 2 summarizes what we have seen above. So suppose that A is a diagonalizable matrix, which is given by PDP inverse, where D is the n by n diagonal matrix. And suppose that B is the basis for Rn, formed by the columns of P, then D is the B matrix for the transformation, which is given by the multiplication by A. Or in other words, we can represent linear transformation defined by the matrix A as a multiplication by a diagonal matrix. So let's look at the first example. So suppose that A is given by 3, 2, 1, 2. And in the previous section, we have seen that we have eigenvalues equals to 4 and 1. And the eigenspaces are spanned by these two vectors. Then we can form P equals to 2, 1, 1, negative 1. So I just put the eigenvectors into the columns. Then D equals to the corresponding eigenvalue. So the first column corresponds to 4. So we have 4. And the second column corresponds to 1. So we have 1 over here. And the rest are zeros. Then we have P inverse equals to 1 over, so the determinant is negative 2 minus 1. And the adjugate is negative 1, 2, negative 1, and negative 1. Where this gives you negative 1/3, negative 1, negative 1, negative 1, and 2. Then we have A equals to PDP inverse. Then we can conclude that the B coordinate for T equals to the diagonal matrix, which is given by 4, 0, and 0, and 1. Now, if you have a linear transformation with its standard matrix given by A, 7, 2, negative 4, and 1, then finding a basis that makes the B matrix for T is diagonal is equivalent to find the eigenvectors of the given matrix. So we want to find the eigenvectors for A. So let's pause the video and try to find the eigenvectors of the given matrix. Okay, so let's work on this problem together. So to find the eigenvectors, we have to find the eigenvalues. So we have to consider the characteristic polynomial or the characteristic equation. So the determinant of A minus lambda I equals to, I guess, the determinant of 7 minus lambda, 2, negative 4, and 1 minus lambda. But this equals to 7 minus lambda, 1 minus lambda, and I guess plus 8. And if you simplify this, you will get lambda squared minus 8 times lambda plus 15. Or if you do the synthetic division, you will get lambda minus 3 and lambda minus 5. So letting this equal to 0 gives you lambda is either 3 and 5. So when lambda is 3, eigenvectors corresponds to the spanning set of the null space of A minus 3i. So this equals to, I guess, 4, 2, negative 4, and negative 2. And this is row equivalent to, I guess, 2, 1, 0, 0. So from here, we get the solution set x equals to negative 1 over 2 x2 and x2, or x2 times negative 1 over 2, 1. And for lambda equals to 5, well, A minus 5i equals to, I guess, 2, 2, negative 4, and negative 4, where this is row equivalent to 1, 1, 0, 0. So you get the solution set to be x2 times negative 1 and 1. So from 1 and 2, we get two eigenvectors. So the basis that we're looking for is B, that is given by negative 1 over 2 and 1, and negative 1 and 1. Okay, so the theorem above actually holds even if A is not diagonalizable. Suppose that A is given by this 2 by 2 matrix. So let's pause the video and try out part A and part B before I give you the solution. Let's briefly sketch the solution for this problem. So first of all, to see whether A is not diagonalizable, we have to find the dimensions of the eigenspaces, or you want to find all the eigenvalues of A first. So basically, you want to let the determinant of A minus lambda I equals to 0. Then this gives you the only solution lambda equals to -2. So to be able to diagonalize, we need two different eigenvectors. However, if you calculate the eigenvector for lambda equals to -2, then we get only eigenvector, well, that is spanned by 3 over 2 and 1. So because we have less number of vector to build P, we get A is not diagonalizable. And this is because P has to be n by n matrix, and in this case has to be 2 by 2 matrix. However, with this matrix, if you calculate P inverse times A times P, then you will get a triangular matrix. So first of all, we have P inverse equals to 1 over the determinant, which is given by 3 minus 4, and 1, 3, -2, -2. And this equals to -1 times 1, -2, -2, and 3, or this equals to -1, 2, 2, and 3. So if you calculate P inverse AP, then this equals to -1, 2, 2, 3, and A is given by 4, -9, 4, and -8, and 3, 2, 2, 1. And if you calculate that, then you will get -2, 1, 0, and -2. So you have 2's in the diagonal and 1 in the upper triangular part. So even though we cannot make the given matrix as a diagonal matrix, but we can still make it close as possible to be a diagonal matrix. So we call this matrix B as the Jordan form of the given matrix. And in fact, every square matrix A is similar to a Jordan form of the given matrix. And there are a lot of theories about the Jordan form of the matrices, but we won't be able to cover that in this section. Okay, so we won't cover this section in detail, but I want to give you some ideas about what complex eigenvalues mean. So complex eigenvalues are eigenvalues which are complex numbers. And the point of this section is the eigenvalues of the real valued matrix can be complex numbers. So let's consider a matrix A which is given by 0, -1, and 1 and 0. And this is the standard matrix for the clockwise rotation by 90 degree. So if you rotate things by 90 degree, then are there any vectors that are sent to multiples of themselves? Well, everything is rotated, so there are no vectors that are sent to multiple of themselves. In this case, if you calculate the characteristic polynomial or determinant of A minus lambda I, then this gives you -lambda, -1, 1, and -lambda. And this equals to lambda squared plus 1. So if you let this equal to 0, then there's no real solution because lambda squared is -1. But if you allow the complex numbers, then we can tell lambda equals to plus minus I. So eigenvalues exist if A acts on C2 instead of R2. And in that case, we can find the eigenvectors corresponds to each eigenvalues, I and -I. So by definition, you want to consider the null space of A minus I times I, which equals to -I, -1, 1, and -I. And if you subtract I times R1 from R2, then this gives you, I guess, -I, -1, 0, and 0. Or in other words, we get -I times x1 equals to x2. Or if you multiply by I for the both sides, you get x1 equals to I times x2. So we get the solution set to be I x2 and x2, or x2 times I and 1. And for negative I, we consider the null space of A plus I times I, and this equals to I negative 1, 1 and I. And if you add I times R1 to R2, then this is row equivalent to I negative 1, 0 and 0. So this gives you I times x1 equals to x2, or x1 equals to negative I times x2, and just multiply by negative I for the both sides. Then this gives you the solution set to be negative I x2 and x2, or you get x2 times negative I and 1. So we get eigenvectors as I and 1 and negative I and 1.